For these last two examples, you're given that you have a power function, and you're asked that based on what you see in the graph, is it a situation where the p-value is even or odd, whether a is positive or negative, and then to actually find the value of a based on knowing it's a power function. So for this first one, the fact that you see that the two ends, the end behavior of this graph, are both pointing in the same direction is an indicator that this is going to have an even power for p. So p is going to be even for sure. Now, because you know it's an even power and the two ends are actually pointing up in the positive direction, that tells you that a is going to be positive. Now, if you're unsure about that, when you actually calculate a value, and usually one of the best values to choose is when x is 1, see what happens there, because that's going to help you figure out the value of a, whereas other situations may not do so well under the circumstances. But here, you know that you have the point 1, 2 being on the graph. So you know that y is 2 when x is 1. That means that for that to happen, because 1 raised to any power is just 1, you're going to have a being 2, and so that's what it is. And you can see that that is a positive result. Likewise, for this example, now another power function, these are pointing in opposite directions for the end behavior. And that indicates that you have an odd exponent for p, so it's definitely odd. Now, since overall the graph is decreasing, that tells you that it's going to have a value of a that's negative. If it was increasing, if it was starting low and ending high, then it would be positive. Now to figure out what the value of a actually is, again, using this 0.1 negative 6, you know that the y value is negative 6 when x is 1. Of course, 1 to the p again is just 1 again. So a is negative 6, which also confirms that it's still negative. And so you have the value of that. In the last example, you're given these three graphs. You have f, this linear graph. You have g, this graph right here, looks exponential. And you have h, which looks like a parabola. And you're asked which one of these could be a power function. Well, power function, as you know, is written in the form of y, or whatever, f of x, g of x, h of x, whatever it is, equals some constant times x raised to an exponent. And this is usually an integer exponent. Now, a couple of things about those is that oftentimes for a power function, you're going to see some sort of change in steepness. You're going to see changes in direction. Whereas this one here, it's all one direction and it only changes in steepness once. This looks more exponential, g, than anything else. So we can exclude that one right off the bat as being a power function. It also, when we look at the second thing we're about to look at here, it also fails that one too. Linear functions can be power functions because exponents of 1 do count, but a power function doesn't have anything else occurring other than this constant being multiplied to a power of x. So if x were to equal 0 for a power function, that means that, well, you would have 0 raised to whatever this exponent is, and if you have an exponent, and this is usually a positive exponent, integer exponent at that, you're just going to end up with 0. And 0 times a, of course, is 0. So, and a power function, when x equals 0, y equals 0, so the graph should pass through 0, 0. This linear function does not. I don't know what this number is, but it clearly is not here. And that's another reason why g of x was not a power function either, because its y-intercept is occurring above the origin. H is the only one that has 0, 0 as a point. So that's why h would be the one that's most likely to be a power function. So that is the end of this example, and that is the end of this video. If you have any additional questions, please make sure to bring them up during class.